Hello and welcome again. In the previous class we were discussing stability of amplifiers, and in particular how to make higher order amplifiers are also well behaved. Okay. So, as we have seen, we can do the analytical calculations of the step response for the case where you have an integrator and an ideal delay, and also when you have an integrator and an extra pole, that is a second order system. Okay. But for higher order systems, when you have many extra poles, it is not possible to do analytical calculations, it gets very complicated. Therefore, what we do is we get some idea of how the loop gain should look like from what we know about second order system and the system with the ideal delay, and then apply the same to higher order systems. Okay. Just as a quick summary, when we have a second order system, what we mean by this is that the loop gain is of the form of an integrator with a certain unity loop gain frequency and an extra pole at P2. Okay. We have also seen that this is approximately like having an excess delay of 1 by P2, meaning if you had only the integrator, the step response of the loop gain would be a ramp of slope omega u by k. If you have an extra pole, you will still get a ramp of the same slope, but it will be delayed with respect to the original one by an amount 1 by P2 approximately. Okay. And for this particular system, we know that the system is critically damped for P2 being 4 omega u by k. Okay. Again, this corresponds to a delay, this is equivalent to a delay of 1 by 4 times the time constant of the integration. Okay. And so, this is what we know, and if P2 falls below this, we get a certain amount of overshoot in the step response. Okay. And for a system with an ideal delay, the loop gain is again of the form of an integral with some extra delay. So, and this corresponds to, I mean, this is exactly equal to an excess delay of Td. Okay. So, in this case, we know that the system is critically damped for Td being 1 by E times k by omega u, and if the value of Td exceeds this, we get a certain amount of overshoot, but we had earlier discussed that for Td less than, let us say, half of k by omega u, the amount of overshoot is limited and it may be tolerable. Okay. And similarly, when you have the one extra pole P2, when P2 is greater than about 2 times omega u by k, when P2 is 2 times omega u by k, there will certainly be overshoot, but it will not be significant, and the overshoot is tolerable. Okay. So, what we will do is we look at the loop gain, magnitude and phase response corresponding to these values, which we know are reasonably good, and then make the loop gain of any higher order system correspond to the same. Okay. So, first let us consider the second order system. Whose loop gain is omega u by k divided by s, and in general it is some unity loop gain frequency omega u loop, omega u loop by s 1 by 1 plus s by p 2. Okay. And the magnitude of L of j omega, let us first take the case where p 2 is 4 omega u, okay, and the magnitude of L will be 1 when omega is approximately omega u loop. There will be some contribution to the magnitude from the second term, but it is small enough that we can ignore it. Okay. So, the phase angle of L at the unity loop gain frequency is given by minus pi by 2 due to the integration minus tan inverse 1 by 4 due to the second pole, and the phase margin P m, which is pi plus the angle. Okay. So, this tells you how far you are away from the critical point of minus 1 0 in the Nyquist plot. This gives a measure of how far away you are from that, and this is equal to tan inverse of 4, and this corresponds to a phase margin of 76 degrees. This we have already seen. Okay. So, what this means is, if I plot the Bode plot, magnitude of L and the angle of L, the magnitude of L will have a 20 dB per decade slope, and it crosses unity approximately at omega u loop, and at P 2 it has another break point and it falls down further. Okay. The phase starts from minus 90 degrees or minus pi by 2 due to the integrator, and it starts changing due to P 2. At P 2 it will be minus 135 degrees or minus 3 pi by 4, and finally it goes off to minus pi. Okay. And the phase angle at this point is minus 104 degrees, and the distance from minus 180 degree, which is the phase margin, is 76 degrees. Okay. Similarly, we can evaluate for what happens when P 2 is 2 omega u instead. I will write it here in a different color, and in this case the magnitude of L is 1, not at omega equals omega u loop, but at a slightly lower frequency, but we will still approximate it the same, because just for ease of hand calculations. Okay. This is not as good an approximation anymore, but we will still do that. And now I will calculate the same thing. So, instead of minus tan inverse 1 by 4, I get minus tan inverse half, okay, and the phase margin will be tan inverse 2, and which corresponds to 63 degrees. Okay. So, in this case, as I said, there will be a little bit of overshoot, but not too much. So, in this case the loop gain magnitude will look like that, and it starts going down before, because the value of P 2 is only 2 times the unity loop gain frequency, and the phase also starts lagging a little bit before. Okay. And in this case the phase margin is reduced, and the phase margin is only 63 degrees for P 2 being 2 times omega u loop. Okay. So, both of these are reasonably good values, and we say that our phase margin has to be within this range. Okay. So, in general, if you are not given any further information and asked to design an amplifier, you should design an amplifier whose loop gain has a phase margin of about 60 degrees or more. Okay. So, that will ensure that the amount of ringing in the step response is not significant. Okay. Now, just to confirm our findings, we will do it for the case with ideal delay, for which the loop gain is omega u loop by s, the ideal loop gain, times exponential of minus s T d, which denotes an extra delay of T d. And we know that the critical damping occurs for T d being 1 by E 1 by omega u loop. Now, we see that the magnitude of L of j omega is 1 for omega equals omega u loop. In this case, it is exact, because the magnitude of the second part of the function here is unity. Okay. And the angle of L will be minus pi by 2 due to the integrator minus omega T d, okay, and omega times T d is nothing but 1 by E. Keep in mind that this is in radians. Okay. So, the phase margin, which is pi plus angle of L of j omega at omega being omega u loop, is pi by 2 minus 1 by E radians, which corresponds to 69 degrees. Okay. So, you see that you will get almost the same value. In the other case, it was 76 degrees for critical damping for second order, and in this case it is 69 degrees. It is a small difference, and such a small difference is due to the difference in the detail of the response. Okay. Because having an extra pole is not exactly like having an ideal delay, it is only approximately like that. So, let us again draw the magnitude and phase response to get some experience with this. The magnitude of L, in this case it simply goes off as minus 20 dB per decade, and it crosses unity at omega u loop, and the phase, it starts from minus pi by 2 at very low frequencies. Keep in mind that this is on a log omega scale, so we cannot show 0, and then the phase goes down linearly. Okay. And for critical damping at omega equals omega u loop, you have a phase angle of minus 111 degrees, this is approximately minus 90. So, this is on a log scale. So, a straight line on a log scale does not actually look like a straight line, I have drawn it approximately, and the distance from minus 180 degrees is minus 69 degrees, and this is the phase margin. Okay. And when we first discussed the system with ideal delay in the negative feedback, we also said that we also tried different amounts of delay and saw what happened. Okay. We saw that for a delay of 1 by E times 1 over omega u loop, it was critically damped. For pi by 2 times 1 over omega u loop, it was unstable, and for delay of approximately half of 1 by omega u loop or less, there was ringing, but not too much. Okay. Let me make this instead of 1 by E, I will make it 1 by 2. Okay. So, what happens now? The magnitude of L of j omega becomes 1 at still the same frequency. The second part of the expression does not change the loop gain magnitude, but the phase, instead of being minus 1 by 2 minus 1 by E, will be minus 1 by 2 minus half radians. Okay. So, the phase margin will be pi by 2 minus half, which corresponds to, you know that half of a radian is about 28 degrees. So, this corresponds to 62 degrees. Okay. So, again what we got from the second order system, we saw that in a second order system, when the pole was at 2 times the unity loop gain frequency, the phase margin was 63 degrees. and the pole being at twice the unity loop gain frequency is approximately like having a delay of half of 1 over unity loop gain frequency, and in the ideal delay case that particular delay gives you a phase margin of 62 degrees. Okay. So, the magnitude will look exactly the same as before, the phase angle will be a little more and the new phase margin will be 62 degrees. So, this is for an excess delay of 1 by E 1 by omega u loop, and this is for an excess delay of half of 1 by omega u loop, and this is a good value to remember. So, let us say you are trying to make a negative feedback system whose integrator has a unity gain frequency of omega u loop, that is the loop gain is supposed to be an integration and it has a unity gain frequency of omega u loop or a time constant of 1 by omega u loop, then the excess delay can at most be half of the time constant, okay, and that is a reasonable thing to remember as well. Okay. So, from this we conclude that phase margins of 60 to 70 degrees are good. If you have more, it is even better because it approaches a first order system, but in practice it may be more and more difficult to arrange it, or it may be more and more conservative design if you attempt to do so. But like I said, you should try to aim for a phase margin of around 60 degrees to avoid significant ringing in the step response. Okay. So, now what does it mean for higher order systems? Let us see. So, we will make a table with the order, and let me start with first order, the simplest case, and the loop gain in that case will be simply omega u loop by S. Okay. And we can ask the question whether it is ever unstable. Here by instability I mean poles in the right half plane when you put this in a negative feedback loop. And we know that this is unconditionally stable and it will never happen like that. And we can also ask when it is at critically damped, and for this particular system it is irrelevant, there is never any overshoot in the step response, the step response is of first order, and the phase margin is always 90 degrees. Okay. Now, we can look at the second order case, again something we have already analyzed. And this also is never unstable, in that if you put this in a closed loop, the poles never go into the right half plane, although they can get very close to it. And this is critically damped for P2 being 4 times omega u loop, and for this the phase margin, and let us say we look at phase margin for critical damping, okay, and this will be 76 degrees. Okay. So, now we can look at higher and higher order systems. Now, remember I am looking at 2 extra poles beyond the integration, and those 2 poles can be anywhere, but for ease of analysis I will assume that both the poles are identical. Okay. So, in general we can have a factor of the form 1 by S 1 plus S by P2 and 1 plus S by P3, but it becomes harder and harder to handle analytically, and later from simulation we can see that all those cases are equivalent. So, we will draw our conclusions from this particular one, omega u loop by S 1 by 1 plus S by P2 whole square. Okay. And can this be unstable in closed loop? We will see. So, if we have a feedback system like this, V naught by Vi is of the form G by 1 plus Gh alternatively 1 by h 1 plus 1 by g h. Okay. And the poles will be on the j omega axis if for some particular value of s equals j omega the denominator is 0. So, we will examine the denominator for our case, and remember our loop gain is given by this particular expression. Okay. So, we have 1 plus s by omega u loop 1 plus s by p 2 squared, and this will be 1 plus s by omega u loop plus 2 times s square by omega u loop times p 2 plus s cube by omega u loop times p 2 squared. And if you evaluate it at some sinusoidal frequency s equals j omega, we get 1 minus 2 omega square by omega u loop times p 2 plus j omega by omega u loop. Okay. Remember these two terms give the real part and these two terms give the imaginary part. Okay. Okay. Now, for the denominator to be 0, both of these real part and the imaginary part have to be 0. Okay. Let me copy over this expression. By equating the real part to 0, I get 1 minus 2 omega square by omega u loop times p 2 to be 0, and this says that omega square is omega u loop times p 2 divided by 2. Okay. And the imaginary part being equal to 0, this can be factored out into j omega by omega u loop 1 minus omega square omega u loop p 2 square. Okay. So, this part has to be 0, 1 minus omega square by omega u loop p 2 square is 0. So, omega square is omega u loop times p 2 square. Okay. So, we have two variables here, the actual frequency at which the denominator of the closed loop gain becomes 0. So, the gain becomes infinity, and also the value of p 2 for which it happens. Okay. So, by equating these two, we see that if p 2 is omega u loop divided by 2, these two equations are satisfied, and also omega will be equal to sorry, I made a mistake here. In the parenthesis I should have had only omega square by p 2 square. This is also omega square by p 2 square. So, omega square will be exactly equal to p 2 square. Okay. So, p 2 will be omega u loop divided by 2, and omega is also equal to omega u loop divided by 2. Okay. So, I made a slight mess in the algebra, but this is the final answer. Okay. So, what this means is that there is closed loop instability, there can be closed loop instability if p 2 equals omega u loop divided by 2, and I will not show the other analysis here. It turns out that if p 2 is more than this, the poles will be definitely in the right half plane. Okay. So, this corresponds to an excess delay that is very large, and in this case, so it can be unstable, that is the poles can be in the right half plane, the poles of the closed loop system, okay, and that will happen for P 2 being omega u loop by 2. Please notice that in this case the non-dominant pole has come inside the unity loop gain frequency, or if you think of it as a equivalent delay, the delay will be 2 by omega u loop or twice the time constant of the integration. Okay. So, this we know is too much of a delay, and in this case it gives you instability. Where should the pole be so that we can get no ringing? So, again as I said repeatedly, it is not easy to calculate the time domain response. So, what we do is we make sure that the phase margin is 76 degrees, based on the guideline we get from second order systems. What we mean is that when the magnitude of loop gain becomes 1, the angle of the loop gain should be minus 90 minus 14 degrees, that leaves 76 degrees of phase margin. Okay. And if you compute it for that, we get P 2 to be 8.1 times omega u loop for 76 degrees phase margin. Okay. So, now these two columns are not separate, in that we are not exactly calculating the time domain response without overshoot, but we are looking at a particular phase margin 76 degrees and saying that P 2 is 8.1 times omega u loop. Okay. So, there are a couple of things to notice here. So, first is when there are two extra poles, each of those has to be further away from the unity loop gain frequency compared to when there is only one extra pole. So, when there is only one extra pole, it has to be at 4 times the unity loop gain frequency. When there are two, they have to be at 8.1 times the unity loop gain frequency, approximately twice as far. Okay. So, that the combined effect is roughly the same. Okay. The same exercise can be carried out for higher order systems. And in this case, we have 3 extra poles all at P 2, and this is again for analytical convenience, and P 2 has to be greater than I think 1.125 omega u loop. Notice also that here P 2 had to be half of omega u loop, and here it is more than omega u loop, and then it will be unstable, because the more poles you have, each one contributes an excess delay, and the excess delay contribution due to each pole can be smaller while still driving it to instability. Okay. Of course, the instability is an academic concern, we do not even want to get there while designing amplifiers. For good design, we would like to have P 2 to be about 12.2 times omega u loop for 76 degrees phase margin. Okay. And similarly, we can calculate for fifth order, where instead of 1 by s by P 2 whole cube, we have 1 plus s by P 2 to the power 4. So, in this case, it turns out that P 2 should be 16 times omega u loop for 76 degrees phase margin. Okay. So, as you have more and more poles, and we have assumed identical poles, so each of those poles has to be further and further away from the unity loop gain frequency. And in fact, you can see that if you think of each pole as adding a delay, here you have a single pole adding a delay of 1/4 the time constant of the integration, that is in the loop gain. Okay. And here each one has to add approximately 1/8. So, 2 of them combined will add 1/4. Here 3 of them have to add 1/12, and 3 of them combined will be 1/4. Similarly, here 4 extra poles each has to add 1/16, and the combined effect will be at 1/4. Okay. So, this also should confirm to you that each pole acts like a delay, and the delay contributes to ringing, and even more delay contributes to outright instability. Okay. So, just as a quick example, we can see what happens. So, I have shown the response of the first order system. This is simply omega u loop by s, and this it follows the familiar first order response. and I have also shown what we first calculated. With an excess delay of 1 by E, it is critically damped, okay, and this is with an ideal delay, and all the other cases are in between. Okay. In fact, if you look at it, I have plotted with a single extra pole at 4 times omega u loop, 2 poles at 8.1, 3 poles at 12.2. So, all of these things which correspond to 76 degrees of phase margin, and you can see all of them are bunched together somewhere here. Okay. All of these corresponds to 76 degrees phase margin with 1, 2 and 3 extra poles. Okay. So, the only lack of generality here is that when you have 3 poles, all 3 poles are at the same frequency, but that is okay. Okay. So, this also again should give you a confirmation that a 76 degree phase margin is a good number to have, and then you will not have any overshoot. Okay. We can do a similar exercise based on what we learned from the response with an ideal delay. Okay. So, let me paste that here. So, again here what I have shown is the first order, the loop gain is simply omega u loop by S, and that follows the first order response, and the critical damped stuff here is shown in green with excess delay, okay, with an ideal delay of 1 by E times 1 by omega u loop. Okay. Now, what I have done is I have taken one extra pole, like for instance one extra pole at E times omega u loop. So, roughly speaking this corresponds to a delay of 1 by E times 1 over omega u loop, basically the same delay as in this case. And you see that while the response is not exactly the same, it is the pink curve here, it is in the same range. And as you go to higher and higher order systems, when you have 2 poles at 2 E times omega u loop, so each one corresponds to a delay of 1 over 2 E times 1 over omega u loop. So, the two of them combined form a delay of 1 over E times 1 over omega u loop. So, again the same value as this. So, the response is quite close to the green curve, which is with the ideal delay. Okay. And I have taken 3 extra poles and 4 extra poles and so on. So, all of them are bunched together in this area. Okay. In fact, the higher the order, it becomes closer to the response with an ideal delay. Okay. So, all these correspond to a total delay of 1 by E 1 by omega u loop. So, when I mean by total delay, if you have multiple poles, the summation of delay due to each pole. Okay. So, all of them correspond to the same case. So, this again should tell you that if you have a delay of 1 by E times 1 by omega u loop, regardless of the order of the system, you will get a reasonably well behaved step response. Okay. So, we have seen that this translates to, in the ideal case, a phase margin of about 69 degrees. So, again confirming that phase margins of 60 degrees or more are good numbers to have. Okay. And just to complete the discussion, we have looked at what should be the response of different order systems. Okay. So, if you have a second order system, for critical damping, the second pole should be at 4 times the unity loop gain frequency, and if you have 2 identical poles, they should be at 8 times the unity loop gain frequency. So, I am sorry, here it becomes steeper, and if you have 3 extra poles, it falls down even steeper, but for the same phase margin we computed that they should be at 12 times the unity loop gain frequency. So, if you look at the phase plots, the phase of all of them will start from minus 90, and this goes to like that when you have only a single extra pole. Okay. So, that corresponds to a phase margin of 76 degrees, okay, or a phase lag of 104 degrees at omega equals omega u loop. So, this is the magnitude of the loop gain, this is the angle of the loop gain. Okay. Now, the next one, the third order system with two identical poles also starts like this, and then it has a similar phase margin, and finally, it goes to a larger phase lag, okay, goes to a larger phase lag of minus 270, but at this point it has the same phase margin. Okay. So, let me draw it a little more accurately. At 4 times omega u loop, it should touch minus 180, and then it goes that way. And if you look at the red one, it will do the same here, and then it will do this, and it goes even further. Okay. So, the phase at very high frequencies is very different, but the phase when the loop gain crosses unity is the same for all of them, and we have seen that that corresponds to the same kind of step response. Okay. So, this is a second order system, that is a third order system, 2 extra poles, and this is a fourth order system. Okay. Now, we can look at the Nyquist plots. And let me draw the unit circle nice and big here. Okay. So, the loop gain of a second order system does that, okay, and the angle corresponding to this, the angle from here to here, this is 76 degrees. Okay. If you look at a third order system, so I can't show the details very clearly here, but the point is it intersects at the same point, and then it goes and cuts the negative real axis, and then it does that. Okay. But the point is this the Nyquist plot never comes close to this minus 10 point. If it comes close to minus 10, it becomes close to instability. Okay. This is the imaginary versus real of L, the usual Nyquist plot. Okay. And similarly, if you have a higher order system, it does something of the sort. Ignore the details before it cuts the unit circle, and after it cuts the unit circle, it does that and it goes around, but still it is keeping far away from the minus 10 point if you have a phase margin of 76 degrees. Okay. So, that is what the Nyquist picture looks like. So, the ultimate test of stability is the Nyquist plot, because the poles, the condition of poles being in the left half plane can be mapped to the Nyquist plot not encircling the minus 10 point in the clockwise direction. Okay. But assuming that the magnitude is well behaved, that is the magnitude reduces after reduces monotonically, then it goes inside. The reason I am mentioning this is it is always possible to make a weird system with poles and zeros such that, let us say it has a 76 degree phase margin, and after it goes inside it can come back towards minus 10 and then go to 0. It is possible to come up with systems like that, and if you do that, it will be unstable even if the phase margin is 76 degrees. But we are looking at relatively simpler systems where you have either extra poles or some extra poles and extra zeros. In that case, it is safe to say that if the phase margin is 76 degrees, inside the unit circle it kind of goes straight towards the origin and does not come closer to minus 10. Okay. So, the magnitude more or less goes down monotonically. Okay. So, the real problem will be if the magnitude after falling below unity stays close to unity and the phase angle increases, then it will come closer to -1,0. But most of the systems that we deal with will not do this, and this is something that you have to watch out for. In the magnitude response, you should not have a case where you have something like this and then the magnitude is close to unity and the phase angle increases. If you do that, you will end up with a system that has a lot of ringing, but usually we do not encounter this particular case. So, we just ignore that one. Okay. So, the bottom line is for stability, there should be no encirclement, no clockwise encirclement of the -1,0 point by the Nyquist plot. By encirclement, I mean including both the Nyquist plot for the positive and the negative frequencies. The plot for negative frequencies will be the mirror image of that for positive frequencies. Now, we do not want the poles to be merely in the left half plane, they should be far enough away from the imaginary axis, so that the step response does not have significant ringing. For that, the condition is that the Nyquist plot should steer sufficiently clear of the -1,0 point, and for most systems it can be expressed by a single number, that is the phase angle, the angle at which the Nyquist plot cuts the unit circle and how far it is away from the negative real axis. If it is far enough away from the negative real axis, then you are safe, the Nyquist plot will not come close to -1,0. And how far should it be? So, we examined some cases for which we could find the solutions analytically, that is a negative feedback system with an ideal delay and a negative feedback system with whose loop gain is an integration plus an extra pole. In both these cases, we can evaluate the condition on the delay or the pole, so that the step response is well behaved, and for those well behaved step responses, we find that this angle here is from 60 to 70 degrees. Okay. And we also know that if you do not have any excess delay at all, that angle is 90 degrees, because in that case Nyquist plot simply coincides with the imaginary axis. So, we can make a statement then that any phase margin of 60 degrees or more is good, and when you have no further information, you should design for a phase margin of about 60 degrees. Okay. So, like I said, there are also some exceptions. You can always come up with a weird loop gain function which maintains a phase margin of 60 degrees or more, but just after it crosses unity, that is after the magnitude falls below unity, which means that the Nyquist plot is inside the unit circle, because of some zeros it comes close to the -1,0, okay, the critical point, but we assume that in most of our cases it does not happen. So, it is enough to look at the phase margin, but it is always a good practice to look at the actual magnitude plot and see that after it crosses unity, it decreases monotonically or does not hover around the 0 dB point for a wide range of frequencies. Okay. So, this is a summary of discussion of stability for higher order systems. Now, any amplifier that you design is not likely to be first order or even second order, it is going to have a lot of parasitic poles. It can be due to the integrator implementation, it can be due to the feedback network, and it can also be due to the distributed nature of capacitance in a resistor. Okay. So, when you take a resistor, it is not like there is a capacitor attached to it at one end or the other, it is distributed throughout the resistor, which corresponds to a high order system, in fact an infinite order system. So, if you rely on analytical calculations only, it will be impossible to design it for any step response. So, we take guideline from the systems for which we can calculate it and draw the guidelines for other systems, and the guideline is that the phase margin should be more than 60 degrees. Okay. So, and that we have confirmed by looking at the step responses which can be obtained from simulation, and we have also drawn the magnitude and phase responses of these systems. So, you know that if you design an amplifier, your magnitude and phase should look like this. If you do that, you will be safe. Okay. Now, just before we close, a quick note on why we should avoid overshoot. There are many reasons. So, first of all, let us say one of the places where feedback loops are used most frequently is a power supply. The purpose of a regulated power supply is to hold the voltage to be a constant in spite of the load that you connect. Okay. So, if you connect a heavy load or a light load, it should maintain the output voltage to be a constant, and it has a system like this, it has an integrator, and because the implementation of the integrator is complicated, there will be extra poles. Now, what happens is, let us say you change the load to the system. So, that is like investigating the step response. Okay. Change in load is similar to some extra stimulus to the system, and there will be a step response. And now, let us say there is an overshoot. This means that the voltage can go beyond the specified regulated value. Okay. So, that is, if you are supposed to regulate it to 6 volts, the voltage can rise up to, let us say, 6.5 volts. So, now the load, the circuit that you connect, the circuit that you are powering from the regulated power supply is getting a voltage that is more than 6 volts, and sometimes this can be damaging to the system. Okay. And similarly, if it goes below 6 volts, it can lead to some other corruption, like for instance, it could be a memory chip, and if the voltage slips well below the regulated voltage, what can happen is that you have a RAM chip and the RAM does not have enough supply voltage and it could lose its data. So, it is always good to limit the amount of overshoots and undershoots in the transients. Okay. So, for this you have to design the system for a particular phase margin, and that is why it is useful. Okay. Now, one more note about this phase margin. So, from our investigations we said that phase margin of 60 degrees or more is good, but this is not a sacred number. This assumes that the overshoot is an important criterion in the step response of the system. There may be cases where you can tolerate a little more ringing and a little more overshoot. So, there phase margin of 30 degrees may be adequate. So, we will not talk about that as a general criterion, but in specific cases maybe a phase margin of 30 degrees is adequate. Okay. So, do not think of 60 degrees as a sacred number and you should absolutely never ever design it for a phase margin of less than 60 degrees. So, generally to have a well behaved step response, this is the phase margin, but there may be a lot of cases where the ringing in the step response is not of that much concern, and it could be that designing for 60 degrees or 70 degrees of phase margin is too expensive in terms of the complexity of the circuit or maybe the power dissipation of the circuit. In that case, you may well settle for lesser phase margin because it is not critical. Okay. So, I hope that part is clear. I hope you now understand why this phase margin of 60 or 70 degrees is considered appropriate, how it comes about, and so on. Okay. So, as I said, for higher order systems, the same phase margin is used because if when you have a large number of poles beyond the unity loop gain frequency, you can think of each of them as contributing to certain amount of delay, and the total delay has to be limited to a certain value. Okay. So, to conclude, in general the loop gain will be of the form omega u loop by S and a number of extra poles which may not be at the same frequency. Okay. I have taken n minus 1 extra poles, this gives you an nth order system. So, now I will assume that all the poles are sufficiently greater than omega u loop. So, this means that the magnitude of L is 1 for omega equals omega u loop, and the phase angle of this when the magnitude is 1 is given by minus pi by 2 due to the integration and minus summation of tan inverse omega u loop by p k, okay, for k being 1 to n minus 1, and the phase margin is pi plus this is that much. Okay. And let us say we want this to be 76 degrees, and this means that this entire sum has to be about 14 degrees. Okay. So, this is one way to think about it. Alternatively, we can also think about it in terms of delay. So, the total excess delay here is the summation of all these poles, okay, and this has to be limited to some reasonable value, which is either 1 by E times 1 by omega u loop, or if you are willing to relax it a little more, half of 1 by omega u loop, and so on. Similarly, the phase margin criterion is not absolute. So, this could be more than 60 degrees. So, whatever it is, you see that when you have a number of extra poles, all the poles have to be well beyond the unity loop gain frequency. So, that either the phase margin is more than 60 degrees or the excess delay is less than half of 1 over omega u loop. Okay. So, that ends the lecture. So, in the next lecture we will look at how to implement op amps and how excess delay can come in even in that situation.